Hi, I'm Sophia, and today we'll be presenting our ECSC 343 project on design for manufacturability and circuit analysis. This project analyzes a Sallen key active filter with plus or minus 5% component tolerances, examining how these variations affect circuit performance. The challenge was to develop an efficient method to predict the 1 kHz amplitude response and estimate manufacturing yield without relying on computationally intensive simulations. Traditionally, engineers use Monte Carlo simulation, which runs thousands of iterations with random component values. Our approach leverages surrogate modeling techniques, specifically random forest and neural network regression, to approximate circuit behavior more efficiently. As a baseline comparison, we implemented direct Monte Carlo simulation. This required about 3,000 iterations to converge to a mean output of 0.0596 volts with a standard deviation of 0.0025 volts, taking approximately 0.159 seconds to complete.
To measure the performance of our models, we conducted 10-fold cross-validation to obtain the average accuracy, mean square error, and computation time. Moreover, we measured the final training time of each model, as well as the computation time for each number of simulations. Here's our first model, the neural network. Neural networks are powerful models made up of multiple layers of neurons that compute nonlinear functions of multiple input variables. These layers allow the network to capture complex patterns in data. Neural networks are trained using gradient descent optimization, an algorithm that adjusts the model based on a narrow function such as least squares. Thanks to their structure, they enable high-speed computations once trained, and importantly, they act as a universal approximator. Using the MATLAB AI toolbox, we trained a cross-validated neural network model with increasing numbers of training examples, resulting in an accuracy of 98.4% on our best model at 3,000 examples. The results were a mean output of 0.0596 volts and a standard deviation of 0.005 volts, with a convergence of about 900 simulations. Now onto our second model, the random forest.
Random forest is the strongest surrogate model since it balances accuracy and efficiency. It also prevents overfitting while reducing variance and manages to deal with complex relationships, noise, and missing data by capturing a multitude of decision trees. Constructing the model is cost-effective, even with large datasets, which is beneficial when training surrogates. Random forests show feature importance which enhances interpretability. Random forests are less transparent than a single decision tree, and so are more expensive to run with numerous trees, large datasets, or provide less transparency than one.
The code file built a random forest surrogate model to approximate the output of the filter circuit. First, it generates random circuit parameters, simulate the filter's output, and standardize the input data. Then, it trains and cross-validates a random forest model to predict the output. Once trained, the model is used in a Monte Carlo simulation to estimate the mean and standard deviation of the output, showing how the random forest will reduce the simulation time for large iterations.
In conclusion, our study shows that surrogate modeling is highly effective for uncertainty quantification in circuit design. By combining direct Monte Carlo simulation with random forest and neural network surrogates, we accurately analyzed Sallen key filter performance under component tolerances while dramatically reducing computational costs.